Let's consider this number line, and in particular let's look at 1, 2, 3, 4, 5, 6, 7, and we know the number line can carry on, so then we'll look at 8, 9, 10, all the way on as far as we actually like. Now, what we've just considered is the natural number set, also sometimes called the counting numbers. Here you can see the natural numbers written out in set notation, and set notation simply starts with an opening curly bracket and a closing curly bracket, and in the middle we can see that we have 1, 2, 3, 4, 5, and these 3 dots imply that we go to 6 to 7 to 8 and so on. And imagine the number line again. Now these numbers are called the elements of the natural number set. So 1, for example, is an element, 2 is an element, 5 is an element, and so on. Now we can think of all the elements of this natural number set as being in a container, and here you can see there's a container, we'll say it's a bag, and in there you can see we have the elements of the natural number set. Example 1, 2, 3, 4, 5, 6, 7. And of course we can have a lot more in there. In fact, in reality, conceptually, this would have to be a huge bag to stuff all of the numbers in, because of course the natural number set keeps on going on and on and on, getting 6, 7, 8, 9, 10, 1 million, 1 million and 1, 1 million and 2, and so on. So it's all of the numbers from 1 upwards, where you go up in whole steps. There are no fractions, for example, in the natural number set. So 1.5 is not a natural number. 1.33, not a natural number. 23.5, not a natural number. We can also represent natural numbers by an area like this. You draw an area and you imagine that encases all of the natural numbers that belong to the natural number set, 1, 2, 3, etc. If we return to the number line and this time start at 0 and go 0, 1, 2, 3, 4 and so on, continuing along the number line, what we're dealing with now are whole numbers. And you can see here that the whole numbers have been represented in set notation, and you can see we start with a 0, then a 1, then a 2, then a 3, and the 3 dots representing the fact that we can go to 4, to 5, to 6, etc. Now the difference between the natural numbers and the whole numbers should be clear from the set notation. You see that the whole numbers includes all of the natural numbers plus the 0. And that's been represented here by having this outer bag contain the bag that has all the natural numbers together with the additional 0. Of course, we can also represent this by these areas, where here we have the area that represents the natural numbers, and then the outer area, which contains the area of the natural numbers, is the entire area for the whole numbers. An alternative representation is shown here. This is where we have this outer area representing the set of whole numbers and the inner area representing the set of natural numbers. And we can see that the natural numbers are contained within the whole numbers. Returning to the number line, you can see I'm marking off 0, 1, 2, and I could continue in this direction marking the 3, the 4, the 5, 6. I can also go in this direction and mark off the -1, the -2, the -3, and continue in this particular direction. All of the numbers I've just marked off on the number line are examples of numbers that belong to the integer number set. So 0 is an integer, 1 is an integer, 2 is an integer, -1 is an integer, -2, -3. Now with the integer number set, we're not allowed any numbers that contain fractions. So for example, 300.5 is not an integer. -15.75 is not an integer, because those two numbers both have fractional parts. But we should be able to see that integers contain all of the natural numbers, all of the whole numbers, and all of the numbers such as -1, -2, -3, -4. Now what we can do to represent the integer number set against the whole number and the natural number set is to modify this diagram here. and show the area for the integer number set. Now this area represents the entire integer number set, and we can see that it contains the whole number integer set and the natural number integer set. You can see I've drawn the diagram again with a slight modification, and the modification is I've used this symbol here to replace the word integer. Now when we refer to integer sets, this is the symbol that's usually used. Now here's a question for you. What set does the number 1 belong to? Well, let's have a look. We can see it in the natural number set, we can see it in the whole number set, and when we marked off the number line, we saw that it belonged to the integer set. Now that seems reasonable, because if you come here, you can see that if it belongs to this natural number set, it obviously belongs to the whole number set, because the whole number set contains the natural number set. Likewise, it obviously belongs to the integer set, because the integer set contains both the whole number set and the natural number set, and the 1 belongs to the whole number and the natural number set, so it also belongs to the integer set. It is often the case, however, that when people talk about, well, what does 1 really belong to, then it's always said to belong to the one that's the most inner contained in the diagram. So it is frequently said it is a natural number. What about 0? Well, 0 belongs, as we can see here, to the whole number set. It's not in the natural number set, but it is in the whole number set, so that by implication means it is also an integer, because we can see that the whole number area is contained within the integer area. So what about -4? Well, -4 does not belong to the natural numbers, it does not belong to the whole numbers, it belongs to the integer set. So -4 is an example of an integer. Check out the supporting website for these videos, and also consider subscribing to the YouTube channel and get an automatic update every time I upload a new video. Also consider subscribing to the Google Plus circle that relates to these videos.